In this short video, we're going to take a look at two sports-related examples of how a correlational and regression analysis can help with the analysis of some basic research questions. So in this example here, these are the results of the 100-meter dash that took place at the 2009 World Track and Field Championships. And these were data published in a subsequent report in 2011. And we have two sets of data that we will examine. We have the final performance measures of the male athletes in the 100-meter final. And we also have sampled at that time their reaction time to the starter's pistol and measured in seconds. And so the question here is whether an athlete's reaction time to a starter's pistol will be beneficial to their final performance in the 100-meter dash, knowing full well that the score on the left-hand side would indicate that the lower value is the better value because the athlete is completing the 100-meter distance in a shorter period of time, and a lower value for reaction time is a better value because it meant that they reacted much faster to the starter's pistol. And so the first step is to generate the descriptive statistics for both variables in question. And so when we generate the descriptive statistics, we find an average reaction time of 0.139 seconds. But if you look at the table, you saw that not all the athletes had the same reaction time. So we computed a standard deviation of 0.015 seconds and the coefficient of variation using the equation from a previous unit determined a value of 11.01%. In terms of the average 100-meter time, the average score or the average time to complete the distance for the finalists was 9.92 seconds with a standard deviation of 0.23 seconds and a coefficient of variation of 2.27 seconds. So in terms of the variation among the 8 athletes for the performance time, we see that the athletes were grouped much closer together than they were for reaction time. If we observe and try to make that same conclusion from the raw scores here or from the absolute measures here, we wouldn't be able to compare the two. Even though the units are the same, they're actually measuring two different things. But by expressing the variability as a coefficient of variation, we can then see that the reaction time varied much more than the final performance time. So the next step would be to generate a scatter plot of the data with reaction time on the x-axis, because the question has us asking if an athlete with a better reaction time is going to lead to a better 100-meter performance. And so from our scatter plot, we notice a couple of things here. So the first thing is that the reaction time on our x-axis is going to be our predictor variable, and the 100-meter time is going to be our criterion variable. That's what we're trying to predict here. Now, doing the intraocular test, so just by looking at this, we see two very different sorts of patterns that emerge. We see a cluster of data here on the lower left-hand part of the graph, and we have these two lone data points sitting out here. So we'll address these two shortly. But if we just focus on this cluster here of data, we'll ignore these two for now, we see a clear pattern that emerges. And so if we imagine a line of best fit, and we're not going to work through the calculations at this point here, but if we imagine a line of best fit, we would see this line is negative or inverse in terms of its direction. And we also see that these data here are fairly close to the line of best fit. And so this would reveal for the majority of the runners in that race, there's an inverse relationship. And so that inverse relationship would tell us that as the value along the x-axis increases, the value along the y-axis decreases. That is the basic characteristic of an inverse relation. Now we put that interpretation we put it in context to our research question. And so a reaction time that goes from left to right on the x-axis tells us that the athlete was slower to react to the starter's pistol. The value from the top towards the bottom along the y-axis tells us that the athlete had a better performance because they had a faster time to complete the 100-meter distance. So knowing that, our inverse relationship tells us that a slower reaction time, which is indicated by the larger value, okay, so the larger value says that the starter's pistol goes off and it's going to take longer and a greater value for the athlete to react. That's actually a slow reaction time. That correlates with a better 100-meter time. And so just by looking at this, just by examining this conclusion here, we would conclude that a athlete that responds slower will perform better, which is the complete opposite of training techniques for sprinting, where athletes train to have a better reaction time, highlighting the fact that when we conduct a correlational analysis, it does not imply cause and effect. Now, shifting our attention to these two data points here we see this point that sits out quite a bit from this cluster here, and this is what we call an outlier. So the outlier is a data point that deviates vertically from the rest of the data points. And so if we take a look along the y-axis, we see all the data except for this one reside within this range along the y-axis values, and this one is sitting out way above. An outlier could also exist in the opposite direction as well. But if we examine the range along the x-axis, we see that this data point's x value sits, although on the high end of the cluster, is still contained within this cluster. This other data point, we wouldn't call it an outlier. It's what we call a leverage point. And a leverage point, by definition, is that point that has a large horizontal deviation. So if we take a look at this point's y value, okay, their y value does not appear to be that much different than this cluster right here. So its y value is somewhat consistent. However, its x value is very different than the rest of the data, and that's what we would call a leverage point. Another example here when examining how a correlation and regression analysis can bring some meaningfulness to the examination of data relates to what's called the NFL Draft. This is an annual event in which the teams in the National Football League go through a process where they select players for the next season, and these players are graduating university football players. So there are 32 teams in the league that take part in this event. It goes through 8 rounds, where in each round, each team gets to make a selection of an athlete that will become hopefully part of the team. In 2015, a total of 256 players were selected in the entire draft. Now, the players that are perceived to have the greatest value to a team are the ones that typically are selected first when the selection process begins. Now, for the first round selections, it's a very important place for a prospective player because of something called a signing bonus. So a signing bonus is not the salary for the professional athlete. It is a one-time payment that is paid out to the athlete for simply signing a contract with the team that selected the player. So once the player is selected, then negotiations will begin at arriving at a salary structure, but separate from the salary, the signing bonus is paid out to the players, and the value of the signing bonus is proportional to the perceived value of the player. So the player that's selected, in this case in 2015, Todd Gurley, was the very first player selected in the entire draft because he had the highest perceived value as a professional player. So examining the descriptive statistics for the 32 players selected in the first round, the average signing bonus was found to be just over $7.5 million. That's a one-time payment. The standard deviation was found to be almost $4 million. So even though the standard deviation in this case was found to be less than the average, that standard deviation is still quite a bit large for that average that we see there. The median signing bonus, so the median statistic, measure of central tendency, was found to be $6 million. So what we see in this case, we have a median value of $6 million, which is quite a bit less than the average of over $7.5 million. And so when the mean value is greater on the positive side, has a greater magnitude than the median, that tells us that these data are very likely positively skewed because it's the average that gets skewed in the positive direction, and the median will sit between the mode and the mean. And these data were obtained from NFL.com. So, but when we plot the data here, it reveals some interesting findings. So along the x-axis here we see as a function of first round selection, this is not a frequency distribution. Okay, these are plotting the data on a scatter plot. And we have, in terms of the blue diamond symbols here, this is the actual value paid out to the actual player that was selected in the respective rounds. And so here we see the first round player having the highest signing bonus, and we have the last player selected in the first round having the lowest signing bonus. And so what we see here is that if we calculated the average, which we found to be just over $7.5 million, somewhere right around here, we see that only 3 players had a value around that average, whereas the rest of those first round selected players did not have a salary close to the average. And so in some situations, the average is a helpful statistic, but if we only focus on the average, we see here that the average is not a direct reflection of what each player got paid. And so this is important for prospective players because a player that's selected later in the first round will see a lower signing bonus, where the majority of the players, down here on the bottom, so the majority of the players selected in that first round had a signing bonus lower than average, but the average value is skewed into the direction of the higher payouts to a smaller number of players, where the top player, Todd Gurley, was provided a check after he signed close to $17 million. And if you're a player that was selected last in the first round, your signing bonus dropped from potentially $17 million down to around $4 million. And what we see here is this is the regression equation that was generated from a from Microsoft Excel. That is a very different type of equation we observed earlier in lecture. This is called a third-order polynomial function that has a coefficient of determination that is very, very high at 0.97. So this equation here very accurately models and predicts the first round signing bonus, at least in 2015. So this ends this video on some sports related examples of correlation and regression analysis.